Welcome to the last plenary session of this CEDAR workshop. This morning our first speaker has real incentive to be done and out of here because his plane is about 2 minutes after he stops speaking. And so with that in mind, I won't say a great deal. I'll just introduce Jan Soyka, who is going to talk to us the last tutorial, inferring the limitations of numerical.
Josh one day called me up and said, how about doing a tutorial for CEDAR and pick a title to do with models, model errors. And first remark was, of course, there are no errors. Has anybody ever seen a model produce errors? No. So what I did was turned it around a little bit. Hopefully for the students, what we'll end up with is something useful from the tutorial. For us more senior people, it's too late, okay? So what I want to talk about is exactly this. And as we go forward, you'll see where I'm headed. Now, quick overview. We'll have a little discussion of what to expect from this tutorial. And then we'll select a tutorial example. And the example, is going to hopefully itself give you a little education as an outcome of how you would infer limitations or a set of limitations. We'll talk about empirical modeling in this topic, physics-based modeling, numerical schemes or not. And not every numerical model necessarily has an Achilles heel in the numerics. And then what we'll do is we'll see what we've inferred about limitations on this one example. And then we'll leave with an approach that I would suggest for anyone who wants to ask the question, what's the limitation of this model I'm about to use? Okay, so let's have this little initial discussion. Have you used a numerical model? Hands up if you haven't used a numerical model. Okay, yeah, okay, so some people lie automatically, okay, but the bottom line is, in our careers, and you young people, most certainly in your careers, you will be using these. So we're all on board that we want to know a bit more about them. Now, when you did use a model, did you even think about it? Or did you just proceed? Okay, so this is kind of your own selves thinking through this. What did you worry about or didn't worry about? Okay, one more. What did you do about addressing these burning concerns? So here you are, you've been given this model, you ran it. Did you publish right away? Did your dissertation proceed smoothly, etc.? Okay, so here are kind of these three things. And I'm almost sure that most of us did this. You know, you got a model, you respected the person who developed it, and you just kind of went with this. And although this is politically insensitive, we're kind of okay. This is a starting place. So let's do better. Did you ask someone? Well, you asked your mentor, and he or she automatically said it's a darn good model, and you proceeded, okay? Next thing was, well, did you ask the model developer? Now, here's the Achilles heel to this whole process. If you go up to the model developer and say, what's wrong with your model? You've just about set yourself for nothing, yeah? And the whole point of this tutorial is, can you get around that and actually ask these people the correct questions? So that's where we're headed, okay? Okay, maybe a few of us, and I might not be included in that list, read the model paper to see. Now, for those of you who've done this, you know this is not getting you anywhere either. Because by the time you've got a mature model, that 10-page JGR paper cannot contain the information you're asking for. So what do? Well, this is where we're headed today. What you would do is look at the bibliography and work backwards, okay? And that's the point of our tutorial today. How can you learn enough that you ask sensible questions? And then this isn't an unreasonable thing. As physicists, as engineers, taking some time to think about it is not going to be harmful. Okay, so here's our problem. It applies to any model, so we'll call it a canonical black box. Here we are, you've got this model, and the technology is such that it runs. You might worry about the physics in there. You might worry about the observations that were used to get this thing going. what kind of mixture of physics and observations are contained in this model? Then, of course, you're going to worry about how the heck did these guys turn this model into an answer? There's functions, there's formulas, there's equations. And worse still, you're kind of concerned about this entire, is there some weird, sophisticated numerical technique that's gone completely haywire? This isn't a silly thing. Yesterday in John Emmert's workshop, we saw a difference between HWM95 and HWM 2007. And for those of you in that audience, how many of you thought that 2007 was not acting physically correctly? Okay, so there's nobody. Yeah, Aaron. It was just a clear example of numerics in some way gone wrong. And there it was in front of us. And John, one of the developers, stood up and didn't apologize, but said, we'll take it under consideration to figure out what went wrong. So it is possible that that's your Achilles heel. Boundary conditions. We all know equations need boundary conditions. And then there is this other thing. How did they get around all of these things? So here's you sitting there waiting for the answer. And of course, it gives you an answer. The smile tells me you all know the answer already, okay? So of course, you say, no, it can't be. But remember, you're talking to a computer. Yes, it is. So you haven't got any further forward. So let's try harder. So we're going to select a tutorial example and work through it. We'll make some assumptions. So the first thing is modelers like experimenters and other scientists. The development is for one of two reasons. This first one is to add more physics or observations with the honest intent of improving the description and prediction of the phenomena. And that's kind of our going-in assumption, that there aren't shady modelers out there who built things just because they could, but they're doing better. And the other isn't that irrelevant today. Some of these very advanced models have way more physics than you need for practical purposes, and there are stripped down versions. But today, let's just deal with development one. You've got the state-of-the-art model. It's been a historic development project, and you're wanting to know more about it. So the statement is you're expecting this model to be an improvement over earlier models, and if they had to be improved, there was something wrong. So the other way around is what was missing in previous models and what's still been left out, okay? So let's pick a topic, and the topic I want to pick on is the E-region models. Okay, at this meeting, there's been several posters, really nice ones, about the E-region modeling. We also had a couple of sessions where the E-region came up heavy. How many of you know the limitations of present-day E-region models? Okay, great. So you're ignorant. And by the time you're finished, you will know what question to ask Stan Solomon. Okay, that's Stan, are you here? Okay, that's good. So if you do what we're supposed to do then is, okay, so there's lots of ionospheric models, but we're talking about the E-region specifically. You will find that Stan, Solomon, Bailey, Woods, this is one of the most recent attempts at a good E-region model trying to plug all the gaps and things that are amiss. Titheridge has a boatload of work on the E-region. Buonsanto, Solomon, and Tobiska most certainly had an early attempt at getting it right. Rasmussen, Schunk, Wickwar. Lillenstein, Kaufman, and his colleagues, I think, broke the concerns of what do we have to worry about. So this paper is kind of important. And then there's this thing, a Muggleton paper in 1972. Okay. So let's talk about empirical modeling of the E-region, Muggleton. Okay, how many of you have met this gentleman, Muggleton? His name is Lewis Muggleton. What's your first thought about Muggleton? What book am I reading? Yeah, Harry Potter, okay. Okay, where does Harry Potter, who wrote Harry Potter? What nationality is she? Scottish. Where does she live? Edinburgh, Scotland, okay. Okay, so Edinburgh University, Scotland, between this time and this time. A method of predicting FOE at any time and place. And this is the title of a paper this gentleman wrote, and he's got several papers. Yesterday we heard all about ISR technology being developed in 1 year and the whole process over. And Professor Farley talked about being there when it was done. It was kind of awesome to hear this whole thing. Weirdly enough, I'm going to argue that this guy Muggleton, does anybody know Professor Muggleton? No, we don't. But in a way, he is the first model developer for the E region, okay? So it's Edinburgh, and the weird thing is, from 1969 to 1972, I was in Edinburgh as an undergraduate learning physics, while this gentleman was modeling the ionosphere. Guess what I do for a business? I model the ionosphere. And I had no connection with this gentleman. He was in the Department of Electrical Engineering, and I was in physics. And we, of course, engineers and physicists don't talk. But this community is a bizarre community because half of us are probably physicists and half are engineers, okay? Anyway, that's a little bit of irrelevance. Let's get back to moving forward. FO represents, in this nomenclature, the ordinary mode of radio propagation, and that's all that means. It's a frequency, and it represents, this nomenclature, the critical frequency of the E layer, and that's, if you square this frequency in the appropriate units, you get electron density, the peak density, and this is the parameter he modeled. And how do you know that you've gone far enough back in the literature? If you open up a paper and look at the kind of citation or references, if you get back and you're an ionospheric search in literature, and you only have 2 other names other than your own, Edward Appleton and Sidney Chapman, you're pretty much certain that you've gone back as far as you can go. These are the founders of our field, if you like. So here is a paper. It's a series of papers, actually, but he has his own work cited, but basically his work is based on Chapman and Appleton. And I'll just, in talking about the limitations of his early work, let's just look and see what he talked about. I just Xeroxed this and copied this straight from his paper, equation 3 in his paper. Here's our FOE squared. So this is electron density at chi at some solar zenith angle. And it depends on FOE squared, electron density, at the, at a solar zenith angle where the sun is directly above you, times this thing here. So his model is basically a Chapman function. But what he decides to do is, that on its own doesn't quite do the job. So he introduces a little parameter n. It's a power of the Chapman function. And what he's going to do is, using ionoson data, determine n, and hence model all over the globe, anytime, any place, the E layer. Okay, so this comes up with our first set of interesting limitations. When he did the analysis first time around, n for 4 separate seasons, and he had ionosons all over the globe, 0.35, 0.6, 0.3, 0.5. So that itself isn't too big a deal, but he realized he could get an even better correlation coefficient if he used a piece of information Appleton suggested, which was that the ionosphere is sluggish. And for most of us physicists here, the sluggish F layer is one thing, but there is no sluggish E layer on the scale in which he's working. But nonetheless, he got better agreement. In fact, when he did his regression analysis for the same data, he gets 4 quite different coefficients. So looking at that, if that's as far as the field ever got, we can easily argue there's some major limitations right up front. Okay, but his work is kind of important. His time constants we'd pick on and measurements were typically only hourly values. So catching sluggishness with hourly values is a little bit interesting anyway. Okay, but there's a final reflection on this work. While he was working in Edinburgh, and that the other team developing these same numerical models was here in Boulder. Now here, I know we're in Santa Fe, but had we been in Boulder, it'd been brilliant. The 2 teams are the Scottish team in Edinburgh and the boys in Boulder. And between these 2, they were looking at this problem in the early 70s. The reason why you're still interested in this, how many of you used the IRI blindly? Yeah, you're lying to me, and most of you have. Okay, the IRI today, Raver and Belitsa, the thing that's called the CCIR coefficients, and of course there's the RC coefficients too. These guys are the people who created it with the models that we've just been talking about. Monthly median type data. It's pretty hard slog back then. But the basis of this thing that's used universally goes back to Muggleton and colleagues. This I just put up as a statement of his own kind of finesse, if you like. He compared the Edinburgh method with the Boulder method. And what you're showing in these two columns for a variety of ionosphere stations. And just from the names, you can see it's fairly global. The root mean square deviation in megahertz. And the difference between these two columns is about a factor 2. But it's quite impressive that they were claiming that globally, they were getting to within a tenth, at least, of megahertz. And for those of you familiar with ionospheres, a tenth of a megahertz is pretty darn good. And yeah, okay, so Rich is shaking his head, and you should. This is good stuff. Okay, the limitations, Chapman profile concept, production and loss implied, but the physics was just this mathematical function. So let's go into some physics modeling. Lillenstein, Kaufman, and his team decided that what's been missing in some of the earlier models is a proper description of the photoelectrons. The EUV, XUV irradiance, if you're down at a few nanometers, the photoelectrons have enough energy to produce further ionization, significant ionization. And in the region, these guys showed, pretty much not for the first time, but demonstrate how significant it was. Ray, I'm pleased you're in the audience and you have my apologies. I've picked on this particular statement as an indication of where the field was. However, in many ionospheric modeling efforts, no such detailed photoelectron transport equations are solved, and the secondary ionization is then often assumed to be 30% of the primary. And maybe I should not have put Ray's reference here, but they cited Ray. But to be honest, it's worse than that. Remember, we were 1988 here. And way back in the late 70s, there were teams of us around the globe developing the first ionospheric, thermospheric, and coupled models. Ray's team, Bob, myself, Di Reese, and Tim Fuller-Rowell around the world had already these global models. And what were we doing for our E-region? We were introducing these factors. And for those of you who know a little bit about this is a true Achilles heel. And you'll see as we go forward in time, it doesn't get better very quickly. So this is still a problem. It wasn't that we didn't have secondary electron codes. Andy Nagy and Peter Banks and others had excellent codes developed, two-stream codes. It was just how do you drive these codes legitimately? Okay, they realized that the penetration of this XUV, which is the one that generates the secondary electrons, had a very strong altitude dependence. And in their modeling work, this group realized that their boundary was 100 kilometers. And the peak of the E layer is 108 kilometers. It's only a couple of scale heights. And they themselves pointed out that probably their numerics aren't perfect. They have a boundary condition problem. So right away, they're sensitive to that. But what they did do, and which a large number of us then adopted, they generated scaling factor profiles for secondary ionization as a function of the photoelectron energy and altitude. So that's a fix that's computationally fast and very generic. Nowhere at this time did anybody have a systematic 24/7 measurement of the XUV. And you all know today we still are struggling with this problem. So the E region has this outstanding problem. Craig Rasmussen, Bob, and Vince had an interesting paper in the same year. And what they did was they demonstrated in different ways that people do care about the E region. It provides almost all of the Hall conductivity, 50% of the Pedersen. Magnetospheric models absolutely need this and need it much better than even today than we're doing today for MI coupling work. But also thermospheric models that have dynamos. The actual location of these conductivity layers is really critical. So magnetometer inversion schemes too. So that there was this feeling that in 1988 it was really important. But look what these guys did for the photoelectrons. The model deals with secondary electron ionization by generating ion-electron pairs for every 35 eV of photoelectron energy. So we've got the Lillenstein full code, and you've got people doing this, where they're saying you have a photoelectron with 500 eV. How many electron ion pairs will it produce? You divide by 35. But how do you redistribute this information? Okay, so again, very readily you can see the conflicts and the challenges. Okay, the question really is, how do these methods compare? How does it compare with a full transport model? So if the field stopped there, we have some real easy questions to ask the model developers. And that's what I'm doing. We're setting up the questions at the time, and hopefully they get solved as we go forward. This is another Achilles heel in all this work. This is from the Rasmussen paper. Just once again, I've copied what's a standard continuity equation. But instantly, they reduce it to a steady state, production equals loss. And that's, we all assume, is acceptable in the E region. They throw in a momentum equation, which looks horrendous, and let's move on. The thing that they threw at us in this paper and then reappears again and again, and it opens up questions in your mind. A table like this. The photons produce ionization, 3 reactions. Recombination, very simply, is another 3. But then there is this whole story of other reactions that are going on. So in this case, there's 16. And they put all this together, production loss, and get solutions, and we're happy. But all of these have reaction rates and everything. So just at the back of your mind, we'll come back to this idea that E region, this is one of the harder parts of working the E region over. It's not computationally complicated. It's just you have these huge schemes of what's all going on and rate coefficients, okay? Not just one. Okay, the takeaway message. This was what they were really emphasizing to us. These are conductances as a function of energy. Now this end, let's just put up the next view graph. These are our auroral electrons. Fred Rees and others had worked this problem. Strickland and his team had worked on it. So there's lots of other references. And this is our normal MI coupling. But our photoelectrons are down here in this regime. And the neat thing is that the reversal of the Hall to Peterson. So that as you include photoelectrons and include them correctly, you're going to affect this. So that was the takeaway message that was coming from that paper. But the model is primitive. Again, what's their XUV source? How are you driving these models? Okay, I now move forward quickly to 1992. Buonsanto, Solomon, and Tobiska. This is a rather nice paper. These two had independently produced E-region models. Stan had actually used Banks and Nagy's 2-stream photoelectron code. Buonsanto had actually had a different way of doing his photoelectron scheme. But then Kent tried very hard to generate a very good or an appropriate XUV, and this paper debates that quite a bit. Now, the difference between the two really boiled down to something like Buonsanto's scheme had 13 reactions for that table we just saw, as Solomon had 22. So right away we have this new question. The more the better, or adding more, can it do any harm? This question now arises. You've got these complicated schemes and they're different. But how would you know? Do you have to go and ask them? I throw this up and you can't read it, but don't worry, I'll go through it with you. The two quarta S reactions, these two are the same as these two. And this is the description, if you like, for the reaction rates in the two models. And without seeing any details, this doesn't look like this. And how would any reader determine the sensitivity of the final solution to any of these? And when you've got 22 reactions versus 13, how are you ever going to resolve what the truth is, or does it matter or not, okay? So this is another little red herring that you find in these, when you look at these papers. How can you tell? So far we've got Photoelectrons are important. Chemistry, in this sense, is complicated. I now, for the first time, throw at you NO, nitric oxide. We'll talk a bit more about that. We're all using EMSIS. Not entirely true, but EMSIS would be a bottom boundary conditions to TI, GCM type models and other things. But solar irradiance. So you've got now 4 questions that you want to get answers to. Down here, there are comparisons being done. Millstone Hill was starting to produce E-region profiles. And for this Buonsanto, Solomon, Tobiska paper, these are 2 examples, and there's a handful of such profiles. What you're looking at is a log density scale from 10 to just about 11. Anyway, what you're seeing here is a number of model solutions, and the solid dark line with the error bar represents Millstone Hill's observation. And this paper came out very strongly that we can't get the right answer. Okay, we keep on being low. Buonsanto, we'll just jump forward. But Buonsanto, in an earlier paper, 2 years earlier, had argued that scaling EMSIS 86 and increasing XUV irradiance provides agreement with the Millstone Hill ISR data. So there is this history. How many of you have tweaked EMSIS to help your answer? Yeah, okay. Most certainly XUV, since you didn't know it, you're free to do so anyway. So again, you very quickly realize where the weaknesses in this E-region modeling are. Is EMSIS 86 reliable? And we'll come back to that in a second. XUV irradiance, what do we know? Now, it turns out Titheridge has a number of papers that are really illuminating in detail. This is a complicated plot, but it's in a linear scale here versus altitude of the electron density in the region, 100 kilometers to up to about 135. And what he's showing here is, you can't quite read it, but in angstroms, not in nanometers. He's got different wavelengths, and he's looking at the sensitivity of the ionization profile with these wavelengths. And he's working with 80 angstroms down to about 25, which is 2.5 nanometers up to 8, which is the critical XUV that we worry about. And what he's done here is, let's go up here. If you have no secondary ionization, so you're not accounting for the photoelectrons, you find answers, but you're 50% short of this line, this magic line that he was using, the IRI solution, the monthly median value. If you kind of adopt a secondary profile and you increase by 60%, so this is, you take what you thought was the good answer, multiply by 60%, you start to get numbers that look like IRI. What he noticed is a very strong height dependence. Now, as we get good profiles to compare against, the height of this distribution is sensitive to these wavelengths. So again, it's learning that we've got. And at the end of the day, we come back to IRI. Muggleton and the work they're in from the ionosons. Is this truly the appropriate ground truth? He had one more interesting kind of revelation, if you like. Nitric oxide, which isn't in EMSIS, but is a gas that gets generated at high latitudes, gets redistributed after big storms, moves around, but doesn't necessarily get anywhere down to the Arecibo, Jicamarca low latitude regime. Okay, let me just click quickly. NO, if you remove NO, now they have descriptions of NO. If you remove NO, what you find is you automatically decrease NO+. If you remove NO, you increase O2+. And this kind of reverse behavior is completely acceptable when you see the 20 reaction rates that are all interacting. So that it's kind of complicated. At the end of the day, the electron density profile is only affected by about 10%. But this is mid-latitude NO. If we're in the polar regions at high latitudes after a big storm, NO isn't like any of these profiles. It's something way more exciting. And the impact needs to still be determined. Okay, and I throw up at you this first time the word valley. This is an Achilles heel to ionogram inversion, always has been. how much of a valley should there be? And the valley turns out to be perhaps the most sensitive to how much NO you're using in your model. Okay, still no good NO available. I know Dan and Stan have a model, and it's an empirical model, but it's still only a model. Okay, this now comes to some work that involves the student nitric oxide explorer SNOWY. And their approach here was to try to address this XUV. So as we're moving forward in the literature, people are identifying shortcomings, trying to fix it. But 2 to 7 nanometers is one of the photosensor bins. And 2 to 7, Titheridge has already told you, that range is really important. It's going to produce altitude differentiation through the F1 valley and the E layer. Stan himself has a nice paper where he shows that you change the spectral shape in this, you can move the E layer up and down by a kilometer or 2, just by changing the spectral hardness of this bin. Okay, they realized that from all prior spectral irradiance modeling they'd done, with the SNOWY information, they needed to increase things by factors of 2 to 6. But Lilienstein and others had showed that there is no simple number. This scaling number, if you like, should vary with altitude. It's not the same number at 110 kilometers as at the F layer peak. It's a different number, and you need to do some real sophisticated modeling. I show this, and pity Stan's not here, so I could apologize to him right away. What he did was he took one of the profiles from that previous Buonsanto-Solomon study and showed that with the SNOWY data, SNOWY information, multiplying the XUV by a factor of 4, that was his number, he took his original poor fit to the data, which are these crosses, and generated a new solution. And you can't see the new solution because it lies exactly over the data. Now, you might argue we've come full circle. Does 100% agreement of one profile suggest there are no limitations for this model? And of course, the takeaway message is that, well, let's look at it a little more carefully. He used MSIS 86, okay, so there's a little bit of a concern. SNOWY was all to do with NO, but the paper itself didn't allude to how he used NO. So there's an immediate question for Stan. What were you doing with NO? And these analyses mixed things together. The observations were from a 1990 14th January ISR observation, and the SNOWY data came at a much later time. It's almost a half solar cycle apart, you know, so there's a number of reasons why we shouldn't walk away saying that we've done it. Okay. Oops. Okay, I'm just restating there. So numerical schemes or not. Now this one turns out to be kind of rather simple. We're talking about purely a production loss. We've removed diffusion. We're down in the E region. The time constants are usually minutes when the solar zenith angle is reasonable. When the solar zenith angle is near dawn or dusk, kind of terminator, this isn't true. But none of us modelers necessarily worry about that. Should we? Is another thing. But the numerics in this particular example is not what you would hang on and worry about. There are enough complementary models that come out with similar answers. The original Lilienstein one, where he did indicate at 100 kilometers was his boundary, which is ill-defined. By the time you go up 2 scale heights, you might worry that your numerics is still a problem in that case. But more recent models have a much more careful extended altitude range, so it's not the same problem. Okay, so let's just wrap up here the E region tutorial. So you've gone through all these papers, and we would want to know what solar irradiance is going into this model we're about to run. How are they doing the XUV? We really want to know how are they representing the secondary electron production. Down in the E region, this can be anything from a factor of 2 to 6 to 8, depending on what you've done up here with the XUV. So these are burning questions. If you're at mid latitudes, the case could be made NO is not the biggest deal, but if you're at higher latitudes, you'd want the modeler to tell you what they've done. Now, the neutral atmosphere, down at 110 to 120 kilometers. MSIS, yeah, okay. Dawn, dusk, perhaps time-dependent numerics are needed. If you were concerned about running at the terminator, none of these models are probably what you really want. There aren't any really that handle that properly. And did we even mention nighttime? There is a nighttime E region. None of these papers really deal with it. Titherage, empirically, using Chapman-type profiles, models, did deal with nighttime. Oh, by the way, every single model has a nighttime in it, and we just do it fine, so don't worry. Okay, so here we come to, if we want to do better and you really want to know, ground truth is really where you have to go. So this is a little pitch I've used, this is the third time this week, okay, so you're getting used to it. Okay, the first thing is the observations. The historic observations are all with ionosons, and there were many from IGY period, and this is an awesome data set and still is. It can be mined and there's still work to be done. I have nothing against it. Millstone Hill, they did run for many, I don't know many decades, but for many years, very good altitude profiles, but their resolution was 4 kilometers. And in a second, I'll show you why 4 kilometers isn't going to help us. Arecibo, I worked with Mike and Sixto, and we did a special campaign with SDOEVE. And in the last 2 days here, I've learned iSCAT has been running this mode, and interestingly enough, Altair down in the equator has also been running a mode of this high resolution. So you'll see what I mean by this in a second. What we really need to really tie down these models ourselves is 1 kilometer altitude resolution. We need seasonal trends for the profiles. Need all local times, the diurnal variation, and you'll see in a second why that's important. Need many latitudes, okay? So that this problem of the E region, the models are there, and it's really hard to tease out a limitation. It's perhaps easier to reverse the thing and find really good new data. And the new data that's coming online would be ISR chains, all simultaneously observing the E region. I've got a plot in a second, you'll see. And simultaneous SDOEVE observations. SDOEVE isn't perfect. There are limitations. But what it does do is 24/7 monitors the solar irradiance from 0.1 nanometers up to about 125, which just about covers everything we need. But there are a couple of deficiencies that I won't talk about just here today. But nonetheless, it's the first time that if you run your ISR, there is a data set that would drive the modelers in the right direction. You get the photo production, you get the secondary electrons correct, and you're left with things like NO, which may or may not be a problem, and MSIS at the end of the day. Here's the kind of takeaway in this particular problem. This is Arecibo on the 9th of February this year. They run a high resolution mode. This dark red is a mauve color, is a saturation, simply because of my color scale. I want to emphasize the E region. This is solar local time from dawn to dusk. And this is what we would call our E region, the valley, and then the F1 region. The altitude range, this is 10 kilometers. You don't have to squint very hard to realize this is not a horizontal line. The E region is tilted, and the tilt here is 4 kilometers-ish, so that this is significant. Now, it's nothing new. Titherage, very carefully with ionoson data, knew that this was a seasonal trend and everything, but it's out there. But Stan Solomon himself showed that depending on what EUV, XUV hardness you choose, you can move this up and down. So you need the entire data set. Now, interestingly enough, we didn't even mention this. This thing here, you can just about see, and you don't have to squint too hard, is a descending layer, which is a very common phenomena. Talks about wind structures that we're not even modeling. And down here, it's no big deal today. On this particular day, it's sporadic E. So I'm done in the sense of we've talked through an example, a tutorial, and I'd like to think that as you leave, you've got a And for one model, you've kind of got a feel for the limitations, and hence you can address that if you ever have to use it, where you would worry and what questions to ask. I argue that for any numerical model X, you can actually follow the same procedure that we just did. Now, I use the word Google. There's a bazillion databases out there that lets you go through the literature. And you could, in 2 days, I swear, with Google or such a device, find the most recent Model X, and from the bibliography of that, start going backwards. And you only need to go back to Muggleton. Once you hit Muggleton, you're there, right? In every single model development, there's a Muggleton, whether you know him or not. It's not too important, but you can pick up, and I think in most cases you've got half a dozen papers. Now, it's not all the papers and everybody who's worked in the field, but in that way, you can, every one of us, and even the youngsters, there's nothing in your knowledge which prevents you making assessments from the earlier papers of what problems the developer was trying to overcome. So you can very quickly do this. In my case, I used a library. I used Melanie and Shauna, and they generate hard copy for me. And I read over a week 6, 7 papers and a few more. What you need to do then is list the science processes and solution schemes. And that's kind of what we kind of walked through. And the important part here is you yourself construct questions and specific concerns about Model X. This is the one that you've been given, your major professors asked you to use blindly. And now you can actually, from the heritage of that model, see how specific phenomena, processes were actually solved earlier on. Because Model X's paper is only 10 pages long and doesn't contain all of what you need to ask. So this is how you get all of that information from the bibliography search. Now, this is the tough part. You're going to go up to this person, he or she, and ask some really tough questions. So I recommend you politely email the model developer these questions. Give them a heads up. Because the interesting thing is, by the time you do this, you probably know more than the modeler remembers. Yeah, it's a fact, our kind of memories are sort of limited. And this young person's done this in a week, is fresh on top of this problem. And for all of you young people, don't be afraid to do this. A couple of days of your life to find out what IRI really is, or MSIS is well worth your time, because you can do this. And I would tell you for sure, a polite email, even though a tough one, will get answered. Yeah, if it isn't, come back to me and I'll deal with them. Yeah, this, if you've done your homework, you have every right to expect an honorable return. And of course, after you've done this, you've introduced yourself, you're an intelligent young person. There is nothing wrong now with chasing this person down. But don't do this first, because we'll abuse you. We'll answer your ignorant questions. And that's the problem. If you just say, what's wrong with your model? What's the uncertainty? It shows a level of ignorance that isn't correct. Do this, and our kind of tutorial is over. You'll be able to infer limitations and get them addressed. Okay, I apologize to all my friends who have abused in one form or another. I learned all about Mr. Muggleton. His name is Lewis. He's born in Africa. He served in various capacities in Rhodesia and in South Africa before coming to the University of Edinburgh as a department head in the Department of Electrical Engineering. The fact that I was there learning about physics and didn't even realize he was there, so I didn't even meet him. It was all happening and I was there but didn't see it. I'm done. Thank you very much.